Let me begin with Dr. Takehiro Nakamura from NTT Docomo. Let me introduce him very briefly. So would you pull up his presentations? So he's going to talk us about 5G evolution and 6G, and he's SVP and also the manager of a 6G lab, NTT Docomo. He has been leading the R&Ds and the standardizations for all the generation of mobile communications. He published main papers and patents, and he has been one of the key speakers representing the mobile industry in Japan. So let's welcome him.
Hello, my name is Takehiro Nakamura of NTT Docomo. Thank you very much for inviting me to this very exciting event. I'm very happy and honored to join this event. Commercial 5G services have been launched globally. Study and development for technologies toward the evolution of 5G are ongoing, taking into account issues in early 5G services and emerging market needs. In parallel, research focused on technologies and services beyond 5G, 6G, is accelerating throughout the world. NTT Docomo is now very aggressive for 5G evolution and 6G. In this presentation, I would like to explain our vision and the latest activities for them. Next, I would like to share our high-level vision on use cases and the requirement for 5G evolution and 6G. We created an image video to illustrate them. Please watch it.
"5G evolution and 6G. Next generation 5G communication will gradually roll out from 2020. But Docomo already has its eyes on the next decade and beyond. 5G evolution and 6G. This communication technology will make 6 major breakthroughs. Extreme high-speed and high-capacity communications. Extremely wide frequency bandwidths. VR and AR experiences will reproduce the 5 senses, supporting remote communication in many fields. What will be enhanced in particular is uplink communication capacity, personal information such as vital signs, real-time big data. All real-world information will be swiftly transmitted to cyberspace for processing to support the development of industry and enrichment of people's lives. Extreme coverage extension. High-altitude pseudosatellites or HAPS and drones will be utilized to achieve 100% coverage. The communications environment will even extend to the sea, sky, and space. Extreme low power consumption and cost reduction. The use of distributed network technology through access points installed everywhere will considerably reduce power consumption and cost. Extreme low power consumption devices will charge wirelessly. You don't have to worry about their batteries running out. Extreme low latency. The communication speed will be much faster than human response time. Sensing technologies will easily make instant decisions. And interactive services that read human facial expressions will become possible. Extreme reliable communication. It will be possible to customize 6G networks for mission-critical industries. There will be utmost security and safety for industries where one cannot afford to make mistakes. And people will be freed from difficult and dangerous tasks. Extreme massive connectivity and sensing. This will enable simultaneous connection of 10 million devices per square kilometer. Advanced networks will use radio waves to detect and accurately locate objects within several centimeters. The resulting high-quality data will be useful for various applications. Smart societies are just around the corner. Technologies that enrich human life. 5G evolution and 6G. Together, Let's enter the future.
Okay, I hope you can understand our concept on 5G evolution and 6G clearly. This slide shows technical components for 5G evolution and 6G. We can consider many technical components, and we listed 8 major components here. New network topology should be studied to extend and improve coverage efficiently and with low cost, especially for higher frequency bands. Non-terrestrial network with HAPs and satellites. This is essential to realize 100% geographical coverage and to extend coverage to sea and sky. URLLC, especially for non-public networks, should be enhanced to meet emerging market demand and a variety of new use cases. Integration of various wireless technologies should be expanded to provide wireless services to users with higher performance and a lower cost. Frequency extension to exploit higher frequency up to terahertz level with very wide frequency bandwidths is very interesting and important topic to meet requirement on very high data rate and capacity. Further enhanced massive MIMO and wireless technologies such as distributed MIMO, new waveform, new duplex scheme should be studied to enhance radio performance. AI can be used to improve radio performance and should be studied more widely and deeply. Network architecture should be advanced and more flexible to cope with increasing use cases and traffic explosion. We have studied and conducted trials on IRS for years. Metamaterial reflector is a useful solution to expand coverage into non-line of sight region. Transparent dynamic metasurface can realize dynamic control of transmission reflection ratio. Now, we are investigating very interesting material, metasurface lens. I'd like to explain this. In the outdoor to indoor scenario, as you all know, indoor coverage, especially for millimeter wave, is likely to be poor due to the high penetration loss of walls and windows. The metasurface lens is a film-type radio lens that can receive radio waves across the window and focuses them. Installing a repeater at the focal point, this lens can be a very strong tool to improve indoor coverage. And also dynamic focus control can be implemented. We have already developed the prototype of the lens and conducted experiment to evaluate gain of the lens. Next, I'd like to introduce another very interesting solution to improve coverage for millimeter wave, so-called pinching antenna. Dielectric waveguide is used for the pinching antenna. Dielectric waveguide is known as one of transmission line and effective for higher frequency because it has a very low propagation loss and it's very slim compared with conventional metal cable. A dielectric waveguide has a very interesting characteristics. It works as a leaky wave antenna by attaching other small dielectric pieces on it. We can attach the pieces by pinching, and then we call it pinching antenna. The benefit of the pinching antenna are shown on the bottom right of this slide. We can deploy and change communication area very easily and flexibly just by pinching a suitable point on the waveguide. We can provide a stable millimeter wave communication areas for use cases which area need to be deployed temporarily or changed frequently, such as construction site, office, factory, in-vehicle. We expect that pinching antenna will be useful not only for millimeter wave, but terahertz deployment toward 5G evolution and 6G. Now, I'd like to show a video of pinching antenna demonstration. Please watch it. I hope you can understand the interesting characteristics of pinching antenna. From here, I'd like to explain frequency bands for 5G and 6G. 5G now supports frequency bands up to 52.6 GHz, and it will be extended to approximately 90 GHz. 6G should cover legacy bands, low, mid-band, and millimeter wave. And also, 6G should exploit terahertz wave up to 300 GHz, and remarkably wider bandwidths to achieve extreme high data rate exceeding 100 Gbps. We should develop experimental systems and conduct trials to evaluate performance of 6G technologies. However, it is premature to do it, and it is difficult to evaluate 6G system performance with many user equipment and at wide area by trials at real fields. Therefore, we developed 6G real-time simulator. Objective of the 6G real-time simulator are visualization of Docomo's 6G technical concept, use as a tool for quantitatively evaluating and appealing the effectiveness of 6G key technologies. We implemented technical topics in the simulator such as new radio network topology, coverage extension technology including NTN, frequency extension and improved spectrum utilization technologies, further advancement of the wireless transmission technologies. With this simulator, we can evaluate downlink throughput performance. Ray tracing technique is used for radio propagation. We can evaluate 5G performance as well as 6G so that we can compare 5G and 6G. Frequency band for 5G and 6G are 28 GHz and 100 GHz respectively. Frequency bandwidth is 400 MHz and 8 GHz for 5G and 6G respectively. Massive antenna is used, and more massive antenna elements are assumed for 6G as shown in this table. We developed two scenarios for evaluation, shopping mall and factory. Due to limit of time, I will show the shopping mall scenario only in the next slide. I will show a screen capture video of 6E real-time simulator. The video will start with simulation of 5G and will switch to 6E. BS antennas are set at high position of the shopping mall to have line-of-sight environment as much as possible. Left bottom graph shows the ratio of UEs classified by downlink throughput. Okay, let's start. This shows simulation result of 5G. In the left bottom graph, light blue means 1 to 10 gigabps. This means that downlink throughput of all UE is 1 to 10 gigabps with 5G. Now, the simulator switched to 6E. More massive antenna is used for 6E. Please look at the left bottom graph. As you can see, red, blue, and yellow colors appeared. Red means over 100 gigabps. This means that around 70% of UEs can experience 100 gigabps or more with 6E. Though higher propagation loss at very high frequency band 100 GHz, very high performance can be achieved thanks to higher beamforming gain and much wider frequency bandwidths. With this simulator, we can see that 6E can achieve big gain potentially. As you see in our promotion video on 5G evolution and 6E, coverage extension is one of very interesting and important topics. Conventional terrestrial network cannot be the solution for drastic coverage extension to all over the terrestrial area, sea, and sky. Non-terrestrial network, so-called NTN, is the solution for it. We can have three kinds of approaches for NTN: ZEO, LEO, and HAPS. ZEO satellite communication services are being provided all over the world, including Japan. Very wide coverage service can be provided by ZEO. On the other hand, performance in terms of data rate and latency is not so good due to very long distance, 36,000 kilometers. LEO is a very interesting solution now. Several major companies have launched so many satellites already, and it is expected that LEO communication services will start in near future. HAPS, High Altitude Platform Station, is also very interesting solution. We can expect very high performance with HAPS thanks to very short distance, 20 kilometers. We developed another simulator, HAPS simulator, to evaluate performance of service link and feeder link of HAPS communications. This simulator has features to evaluate the technology of interference reduction and frequency sharing, to calculate the system capacity and according to various environments on the ground, such as construction area, ships on the sea, and to calculate the communication parameters required to realize various HAPS use cases. We assume 50 km of the maximum distance of the feeder link and the service link. Major parameters are shown in the right table. Frequency is 4.5 or 38 GHz. Frequency bandwidth is 100 or 500 MHz. Okay, let's watch the screen capture video of the HAPS simulator. This is a screen capture video of the HAPS simulator. You can see two HAPS on the screen. Each HAPS is supporting multiple connections for a variety of environments. Frequency is 4.5 GHz and the frequency bandwidth is 100 MHz now. Connection capacity per HAPS is around 4.5 Gbps. Now, frequency is switched to 38 GHz. Spectrum bandwidth is still 100 MHz. Due to higher propagation loss, performance is lower than that of 4.5 GHz, around 3.1 to 3.3 Gbps of capacity per HAPS. Now frequency bandwidth is extended to 500 MHz. Thanks to wider bandwidth, performance is improved to around 13 to 14 Gbps. Now the simulator shows construction area. As you can see, about 0.5 Gbps connections can be provided to 3 construction vehicles via an on-site mobile base station. That is my presentation. I showed Docomo's concept of 5Z evolution and 6E and our preliminary study results. I hope you have an interest in my presentation and I can have another opportunity to provide update on our activities for 5Z evolution and 6E. Thank you for your attention.
Thank you, Dr. Nakamura. It was a really interesting presentation, especially for all the simulator for 6D real-time simulators. And it was really amazing to see 4,600 antennas for shopping mall on the 100 gigahertz. That was really interesting. And I think to implementing this one is really challenging, I think. But it was a really, really interesting presentation. Thank you so much. Thank you.